Good morning, guys. Welcome back to lectures on electrodynamics, and this is chapter 5, and this is the first video for this chapter. Again, our main reference for this lecture is Introduction to Electrodynamics by David J. Griffiths, and this book is highly recommended for you, so get a hold of this one. So we will be dealing with magnetostatics. And of course, we start with Lorenz Force Law, and we will introduce magnetic fields in this lecture. As for electrodynamics, we just have to have a collection of charges, and we call that source charges. And if you want to calculate the force they exert on some other charges, Q, for example, here, we just look at each charges, calculate the force for each one, and then by superposition we can get the total force that is exerted on this one. But what happens if the charges are now moving with respect to the charge in consideration, or the test charge in consideration? Now let's look at this experiment. Two wires hanging from a ceiling a few centimeters apart, and when the current is turned on, so it passes up one wire and back down the other, the wires jump apart. They repel each other here. And when the currents are in the same direction, they would they would attract here. And if they are in opposite direction, they would repel. What could be the explanation for this? Unlike in electrostatics, you have attraction of two different or opposite charges, and attraction of two different or two opposite charges, and repulsion of the same type of charges. But in this case, you have wires. If you have opposite velocities or opposite current in a wire, in opposite currents in the two wires, they will repel. And if they do have the same direction, the current, they will attract. Why is that? Because what is actually doing the attraction or repulsion there is the magnetic force. And we have to note, by the way, a stationary charge produces only an electric field in space around it. A moving charge generates in addition a magnetic field B. And between electric field and magnetic field is easier to detect, and this is actually detected using a compass. But however, you can only detect magnetic field's direction, but not the magnitude. However, you can compare magnitude. If the deflection is away quick, then that is a stronger magnetic field. Deflection of the compass, and if the deflection is very slow, that's a weaker magnetic field. So if you put a tiny compass nearby a current carrying wire, you will discover that the field does not point toward the wire nor away from it, but rather it circles around the wire. So if you have a right hand, if you grab the wire, your thumb, and with your thumb in the direction of the current, then the fingers curling the wire would be the direction of the magnetic field. So that is the explanation why current carrying wires with the same direction, they attract. So look at this figure, the attraction of a nearby parallel current by the other current. So at the second wire, the magnetic field points into the page, for example, and the velocity of the charge is upward. The resulting force is going to be going to be to the left. So the first wire will have to attract wire 2. And by the way, this this is for this current, this is the direction of the wire, and this is the magnetic field. They're always perpendicular to each other in the force here. So the velocity is always perpendicular to the magnetic field, the force is perpendicular to the magnetic field, and the force is, I mean, sorry for that, the force is perpendicular to the current, and the force is also perpendicular to the magnetic field. So looking back at the figure, you had V, or the direction of the current, or the velocity of the charge, and B, the magnetic field, and F, you have mutually perpendicular vectors. And you would think that this could be operated by a cross product. And if you're thinking that, you're right. Exactly. Experimentally, the magnetic field in a charge moving with velocity v in a magnetic field B is given by this. And by the way, B is actually a pseudo vector, and this is known as the Lorenz. That is the magnetic field. The whole thing here, the whole formula is called the Lorenz Force Law. So let's say, for example, now we have a charge moving in this direction. Let's say Q, and then so the speed is also going here, and magnetic field in this direction. So let's make another color for magnetic field. So for example, magnetic field is in this direction B. So what is the force? The direction of the force. Using your right hand, you'll be able to get the direction of the force. You just have to cross V to B. So if you cross V to B, your force would be here. Your force would be here. And by the way, F and V should be perpendicular, P and F should be perpendicular, and B and V should be perpendicular. So let's try another case. So say for example our V is in this direction, and our B is in this direction, and so if these are perpendicular, they are exactly in the same plane. So use our right hand to cross V to B. So here our we cross V to B, and so our direction of the magnetic field would be pointing out of the page. Try it with your right hand, pointing out of the page. So that is the direction of our magnetic field. So you can do experiments with your hands and with your right hand to determine the directions of these vectors and get familiar of them. In the presence of electric and magnetic field, the net force on Q would be this, because the charge would have to naturally exert electric field, and if it is moving, it would now be exerting magnetic field. So in this case, you have E in the same direction as your F, V is perpendicular to F, and B is also perpendicular to F. So therefore, E and B should be perpendicular to each other. Now let's go to the first example. So let's talk about this example. This is about cyclotron motion. The archetypical motion of a charged particle in a magnetic field is circular, with the magnetic force providing the centripetal acceleration. So in figure 5.5, you have here a particle. This is a particle here, a charged particle, because a neutral particle will never be affected by magnetic field. Only the charged particle are affected by the magnetic field. That's why you have this. So if Q is 0, then force would be 0. So you should have a charge. So the charged particle would be moving with speed v, and the magnetic field in this case is in the z direction. So if your z direction extends to here, your magnetic field would be, of course, in that direction. And what is the force? So if you erase this, the force would be in this direction, B. So you will cross V to B. You will cross your, to get the force using your right hand, cross V to B. So using your right hand, put the palm in the direction of V and then cross it to the direction of B. And so your thumb will now point to the direction of the force. So the force is going to the center here. So let's check. V is perpendicular to B, and yes, because in this case your your V, your velocity is in the xy plane, and your B is directed in the Z direction. So it's perpendicular, and of course your F would have to be perpendicular to V and at the same time perpendicular to B. So that is the force that you will be able to get. So in this case, if you have a charge moving that way, and if you look at this figure, if you look at this motion in through the Z axis, you'd really find a circle, and the charge would just be moving in a circle with radius r. So that is the cyclotron motion. So that's in figure 5. A uniform magnetic field points into the page, that's on the Z direction. If the charge moves clockwise with speed v around a circle of radius r, the magnetic force points inward and has a fixed magnitude QVB. QVB, why is that QVB? Because your force is equal to Q times V cross B, and the magnitude of force here is equal to Q times VB sine 90, because they are perpendicular, and sine 90 is equal to 1. So your magnitude of force would be QVB or in this case capital QVB. So that is the force that sustains the uniform circular motion of the particle of charge Q. And now your QVB, this is the force to the center, and the force to the center is also what we call centripetal force. And centripetal force, back in your your study of mechanics, your centripetal force is equal to MA. But your acceleration here is equal to V square in circular motion, V square over R. So if this is your force, and this is now equal to QVB, this one. And if MV is your momentum, so you can write M square V square. You can actually write this as, let's erase this. So your mv square over r is equal to m square v square over mr, so that this will be as this one. This will be p square over mr, and of course this is equal to qvb. Oh, I'm sorry, I did not use this p square. I just have to cancel v. Anyway, you can cancel v here so that you will just use p, because here you have mv. So therefore your momentum of the charge would be this, q times b times r. And this is what we call the cyclotron formula. It describes the motion of a particle in a cyclotron. The first modern, this is modern particle accelerator. So this is the standard means for determining momenta of the elementary particles inside an accelerator. But if your particle starts out with a v parallel to b, this component of the motion is unaffected by the magnetic field, only the motion that is perpendicular to b. And so this will give this will move the particle away such that it will not just move in a circle. If you look at the z-axis, it moves in a circle, but at the same time it goes away from you. If there is an additional speed v parallel, which is parallel to the magnetic field, so it will move in a helix. It moves like in a spring, following a path of a spring, and it goes away with a constant radius going away from you, or going towards you is the same thing if the charge is opposite. The radius is still r, but the velocity in question is now the component of b to v plus, b to v perpendicular. Now let's look at the cycloid motion. A more exotic trajectory occurs if we include a uniform electric field at right angles to the magnetic one. Suppose, for instance, that b points in the x direction and E is in the Z direction, as shown in the figure. A particle at rest is released from the origin. What path will it follow? Of course, you can see the path there as shown already in the figure. But let's look at how the equation of the path was derived. So in this case, your magnetic field is going in the x direction, your electric field is going to the z direction, and the particle is released from here. So initially, the particle is at rest. So the magnetic force there is at first equal to 0 because there is no motion. And the electric field accelerates the charge in the z direction, so it pulls up the charge up. And the magnetic field develops as the charge picks up speed. So the faster it goes, the stronger the magnetic field becomes, eventually it curves the particle back down towards the y-axis. And at this point, the charge is moving against the electrical force, so it begins to slow down. The magnetic force then decreases and the electrical force takes over, bringing the charge to rest at point A, here. There, the entire process commences anew, carrying a particle over to point B, and so on. So the cycle repeats. Periodically. And this is what we call also like an oscillation, but a different kind of oscillation. So there being no force in the x direction, the position of the particle at any time t can be described by a vector zero yt zt. That's the position of the particle at any time t. And the velocity is, of course, you don't have force in x, so it's also 0, y dot, and z dot. That indicates time derivative of those respective positions. So your v cross b, which can be written into a matrix. So this is your speed, and this is your magnetic field. So if you do the matrix operation of determinants, you will be able to get this. So the force will be in the yz direction. So applying Newton's law, you can, so this is equal to, the force is equal to this, and of course this is also the force. If you multiply by q, here, this is also the force. So therefore your force in general would be this, in particular, this is equal to ma, and since the motion is in the y and z, you have acceleration in the y and acceleration also in the z. So if you compare directions y and z, so of course you have 2z here, so therefore you have two equations here, two differential equations in the second order. So we can let q b over m to be the omega. We actually will find later on that this is just the frequency of the motion, or the cyclotron frequency in this case. So the equation of motion then now take the form y double dot equals omega z dot, and z double dot, second derivative, omega e over b minus y dot. So in general, the solution, if you review your differential equation, this will be the solution. Now, the particle started from rest at the origin, which is 0, 0, 0. This double dot y, again, the particle started from rest, which has velocity in the y and z equal to 0. And at the origin, starting point at 0, 0, 0, the y double dot There should be four conditions to determine the constants C1, C2, and C3 and C4. So if you start to eliminate and solve the differential equation, you'll be able to get this and this one for Z, the equation of motion in the y-axis and in z-axis. If you let R equal to E over omega B and eliminate the sines and cosines by exploiting the trigonometric identity here, then we will arrive at this equation. Which is just a formula for a circle of radius r, but this time it is traveling in the y direction at constant speed v, determined by or given by this one. So there's a time dependence in the y, so that your speed would actually be given by r omega. This is in the form y v minus d minus v, I mean y minus vt. So your velocity there would be equal to this, equal to E over B. The particle moves as though it were a spot in the rim of a wheel rolling down the y-axis at speed v, and the curve generated is what we call the cycloid. The overall motion is not in the direction of the electric field, but it is perpendicular to it. One feature of the magnetic force law is that magnetic forces do not do work because magnetic force is always perpendicular to the velocity. For a force to be able to do work, that force would have to be parallel or anti-parallel with the speed, but this time your magnetic force is perpendicular to the speed. So if Q moves by an amount dl, which is v dt, the work done is, suppose this is the work done by the magnetic force, so your F mag would be dotted to dl. Your F mag is this one and your dl is this one, but this v cross b is perpendicular to v. So what becomes of the dot here? That becomes cosine of 90, but cosine of 90 is equal to 0, so everything is 0. Hence you have work done by magnetic force which is equal to 0. Now magnetic forces may alter the direction in which the particle moves, but they cannot speed up the particle or slow that down. So let's now go to currents. The current in a wire is a charge per unit time passing a given point. So it's like time derivative of the charge that passes through some region. So by definition, negative charges moving out to the left count the same as positive ones moving to the right. In conductors, it's only the negative charge electrons that do the moving, and the positive ones just stay in their particular molecule or atom. but it's the same thing. If charges move, I mean, if electrons move to the left, then it's also the same thing as positive charges moving to the right, or vice versa. This is conveniently reflected by the physical fact that almost all phenomena involving moving charges depend on the product of the charge and velocity. So if you change the sign of Q and V, you get the same answer. So it does not really matter which you have. So as used by the convention of the author, we will just use positive charges to be on the move rather than the electrons. So current is measured in coulombs per second or amperes here. And the line charge lambda traveling down a wire at speed v constitute current, and the current is given by this. This is because a segment in the length of the wire, the segment would have length v delta t, carrying a charge lambda v delta t passes point P in a time interval dt. So that's why you have a current there in this form. So in this particular discussion, current is actually a vector, and it points into, it points parallel to the velocity or the speed of the charges, the direction of the speed, so you can actually write current as a vector. In the discussion, however, we're only discussing about only one type of charges moving, but of course if you have positive and negative charges moving, then the total current would be looking like this. But this is very unusual, so we just consider the motion of one type of charges. This is unusual. We would want to cancel either of the two terms. So for a wire which is carrying a current, we have the magnetic force. Of course, this is the original formula, but dq is of course lambda dl, and v times lambda is just equal to I, and of course this I moves with the length, and so the direction of I and dl are both in the same direction. So we can just write also this f mag to be this, putting the direction on dl, not on the I. So if you write this by hand, this would be f mag, magnetic force, integral of I dl cross b. And remember that f mag for point charges is equal to q v cross b. This is for current carrying wire, and this is for point charges. There's no integral here. No integral here. You have an integral because you're dealing with continuous distribution of moving charges. Typically, the current is constant, so you can put that out of the integral, and so your magnetic force would look like this instead of this one. So your I now is outside of the integral. Let's now discuss example 5.3. A rectangular loop of wire supporting a mass M hangs vertically with one end in the uniform magnetic field B, which points into the page in the shaded region in this figure.